We experience our lives as a continuous stream of moments, a river carrying us from a fixed past toward an unknown future. The ticking of a clock seems to be the most fundamental drumbeat of reality, measuring the relentless passage of time. We remember yesterday, but not tomorrow. We feel the profound difference between what has been and what is yet to come. But what if this deeply ingrained feeling of flow is an illusion? The frozen time theory proposes a radical alternative to our common sense intuition. It suggests that the river of time may not be real at all. Instead, it posits that all moments exist simultaneously, past, present, future, frozen in a vast, timeless landscape of possibilities. This idea challenges us to reconsider the very nature of existence. Imagine the universe not as a story that unfolds line by line, but as a complete book where every page already exists. The feeling of time passing, according to this theory, does not come from the universe itself evolving. Instead, our experience arises from a specific process that moves through pre-existing pages, selecting them one by one to form a coherent sequence. This process is called the selector. It traces a path through the static collection of all possible universal snapshots, creating the history we perceive and participate in. To grasp this concept, set aside familiar notions of before and after as fundamental. In the frozen time view, these are emergent concepts, products of how consciousness interfaces with static reality. Each moment, or frame, is a complete and self-contained snapshot of the entire universe. It contains everything: the positions of all particles, the state of all fields, the contents of every mind within that instant. These frames do not come into being or pass away. They simply are. The story of our universe is not being written, it is being read. Next, we'll break this idea into simpler parts. If all possible moments of the universe exist at once as a vast collection of static frames, what explains our experience of living through just one, seemingly continuous history? The frozen time theory introduces a concept to answer this question: the selector. The selector is the process or rule that traces a path from one frame to the next, stringing them together into a coherent sequence. This ordered path of frames is what we perceive as the flow of time and the unfolding of events. The selector is the metaphorical reader in the library of all moments, picking which page to turn to next and thus creating the narrative of our reality. The selector is not envisioned as a disembodied soul or a supernatural being making arbitrary choices. Instead, it is proposed as a fundamental part of the universe's ontology, deeply linked to the existence of conscious awareness. The theory postulates that a transition from one frame to the next occurs in conjunction with a moment of conscious experience. A history, therefore, is not just a sequence of physical states, but a sequence of physical states that are being consciously observed or experienced. The movement of the selector is what generates the subjective sensation of time passing. When the selector is on a particular frame, that frame constitutes the now for the conscious observers within it. The rules governing the selector's path are not random. For our universe to appear orderly and lawful, the selector must preferentially choose frames that are physically similar to the one preceding it. This principle of adjacency ensures that a falling glass appears to move smoothly through space rather than teleporting randomly around a room. The laws of physics, in this view, are not rules that govern how a state evolves over time. Instead, they are constraints on which frames can plausibly follow which other frames in a sequence chosen by the selector. The selector's path tends to follow trajectories of high probability which correspond to what we call the laws of nature. This concept has profound implications. It suggests that causality is not a force that pushes the future into existence from the past. Rather, causality is a pattern of correlation between adjacent frames along the selector's chosen path. The frame of the shattered glass does not exist because the glass fell. It exists as a timeless possibility. The selector simply tends to select the shattered glass frame immediately after selecting the falling glass frames because that sequence has a high degree of physical plausibility and internal consistency. The next step is to understand how this selection process connects to the probabilistic world of quantum mechanics. Quantum mechanics is famously probabilistic. When we measure a quantum system, like the spin of an electron, we cannot predict the outcome with certainty. We can only calculate the probability of each possible result. The Born rule is the mathematical recipe that allows physicists to convert the quantum wave function into these precise probabilities, and it has been verified by countless experiments. A major challenge for any new fundamental theory is to explain where the Born rule comes from. The frozen time theory offers a novel perspective, suggesting that quantum probabilities are not about random events unfolding in time, but about the statistical behavior of the selector as it navigates the space of all possible frames. In this model, the wave function of the universe does not collapse upon measurement. Instead, all possible outcomes of a quantum measurement exist in different frames within the timeless library of moments. For example, in some frames, the electron's spin is measured as up, and in other, equally real frames, it is measured as down. The probabilities given by the Born rule are not about which outcome will happen. Instead, they are about the likelihood of the selector's path proceeding through a frame corresponding to a particular outcome. It is a statistical statement about the distribution and accessibility of frames in the grand cosmic landscape. To make this concrete, imagine the selector is currently on a frame just before an electron's spin is measured. The space of available next frames contains a vast number of frames where the result is up and an equally vast number where the result is down. The theory proposes that a measure, or a way of counting, can be defined over this space of frames. The Born rule would then emerge if the measure associated with the spin-up frames is proportional to the squared amplitude of the spin-up part of the wave function. The selector, following its rules, would then be statistically more likely to transition to a frame from the set with the larger measure. This approach attempts to ground quantum probability in the very structure of reality's frame space. It is not that chance is an inherent feature of temporal evolution, but that the selector's journey through the static landscape of frames has a statistical character. This could potentially solve deep mysteries like the measurement problem by removing the awkward distinction between a smoothly evolving quantum system and the abrupt probabilistic jump that occurs during observation. The collapse is reinterpreted as the selector's transition from a pre-measurement frame to a specific post-measurement frame, a process that is fundamentally part of the universe's structure rather than an ad hoc add-on to the theory. One of the most controversial and intriguing aspects of the frozen time theory is the central role it assigns to consciousness. In standard physics, consciousness is typically seen as an emergent phenomenon, a complex pattern of information processing in a brain that passively observes the universe. Quantum mechanics has long been haunted by the observer effect, where measurement seems to determine reality. Frozen time theory takes that hint, seriously elevating consciousness from passive spectator to active participant. Not just an observer of the film, but tied to the very projector that illuminates it. The selector's movement from one frame to another is intrinsically linked to conscious moments. A history is a sequence of experienced frames. This does not mean a human mind wills the universe into a particular state. Rather, the fundamental laws governing the selector's path must include properties of conscious systems. Choosing the next frame isn't only about positions of particles and curvature of spacetime. It's also about the informational content of minds, their memories, and perceptions of a consistent past. This integration offers a possible way around the measurement problem in quantum mechanics. Copenhagen says an observer collapses the wave function. But what counts as an observer? A human? A cat? A camera? Frozen time avoids the ambiguity by making the selector's path the sequence of experienced moments. A transition to a definite measurement outcome is not collapse by an observer, it's the next step in that observer's conscious timeline. A beautiful and provocative idea is not enough in science. It must ultimately connect with the world we observe. The frozen time theory, for all its conceptual elegance, faces the monumental challenge of reproducing the known successes of standard physics. Any viable alternative must be able to explain the motion of planets, the behavior of subatomic particles. The theory cannot remain a philosophical outline. It must be developed into a rigorous mathematical framework whose predictions can be tested against experimental data. This is where the real work begins, and the hurdles are significant. The first major test is to recover the principles of relativity, special relativity, general relativity. Their core idea: the laws of physics are the same for all observers, regardless of motion, so there is no universally preferred now and no preferred frame of reference. The frozen time theory must respect this principle. Its frames and the rules for the selector's path cannot hide a preferred structure that violates Lorentz invariance. Can discrete frames produce the smooth, continuous relative spacetime of general relativity? Furthermore, the theory must provide a concrete derivation of the Born rule. It's not enough to point to the selector's statistics. The theory must specify a precise measure on the space of frames and a selection rule that together reproduce quantum probabilities. This is the most critical and falsifiable prediction. If no plausible measure and rule reproduce the Born rule, the theory must be abandoned. This is the make-or-break moment where concept meets quantitative physics. Finally, the theory must be consistent with cosmology. Our observations, the cosmic microwave background radiation, the large-scale distribution of galaxies. These provide a detailed history of our universe. The frozen time theory must explain why the selector's path matches a universe that began hot and dense, the Big Bang, and has been expanding and cooling ever since. Thus, the frame space and selector's rules must encode an arrow of time that favors paths from low entropy, highly ordered past states to high entropy, disordered future states. Explaining this cosmic arrow of time would be a major triumph for the theory. The frozen time theory presents us with a radical and unsettling picture of reality, one that forces us to question our most fundamental assumptions. Time caused consciousness. It proposes that the familiar flow of time is not a fundamental feature of the cosmos, but an emergent experience generated by a selector tracing a path through a static, timeless landscape of all possible moments. In this view, the universe is not a story being written, but a finished library of all possible stories, and our life is the experience of one particular path being read. This shifts the focus of physics from laws of evolution in time to laws of correlation between timeless, existing states. The main implications of this idea are profound. Causality is reinterpreted not as a productive force pushing events forward, but as a pattern of consistency between adjacent frames along the selector's path. Quantum probability is recast as a statistical measure over the space of possible realities rather than intrinsic randomness. Most strikingly, consciousness is moved from the periphery of physics to its very center, proposed as an integral component of the mechanism that selects the experienced reality from an infinitude of possibilities. This elevates the observer from a passive witness to an active constituent of the reality being observed. Of course, the frozen time theory is, at present, more of a conceptual framework than a fully fledged scientific theory. The next steps are clear, though incredibly challenging. A formal mathematical model of the space of frames must be constructed. A precise measure must be defined. A clear selection rule must be defined. That rule must derive the Born rule of quantum mechanics and remain consistent with the principles of relativity, and remain consistent with the data from cosmology. These are not small tasks. A long road before this idea can challenge standard models. Ultimately, whether it's correct or not, its value lies in the questions it forces us to ask. It challenges the intuition that time flows, pushing physicists and philosophers to scrutinize the role of time in our theories. It provides a novel, if speculative, avenue for integrating the mysterious role of the observer into a coherent picture of the cosmos. By imagining a universe where all moments are eternal and our experience is a journey through them, we gain a new and humbling perspective on our place within the grand, static, and utterly magnificent structure of existence.